big integer as a value of.
Yeah, that's an excellent example of that as well.
All right, so in this example, this is essentially the same thing that we've built here.
So there are discussions where whether a constructor should throw an exception or not. But
which we are doing, by the way.
But if we extract that to a method, to a function, then you should expect that the function will be able to throw an exception.
Sure.
No and no. Big integer value of long is not the same as piece from notation string. Yes, functions in Java are able to throw exceptions, but if we want to achieve predictable behavior, we should avoid them. The video is really nice. Alexei and Sebastian did a really great job to explain the concept, but there are some stuff that shouldn't be done like that. Let's explore why and how to do it better. To achieve it, I'm going to rewrite the code, explaining all the decisions along the way. So, let's look at the code. I've copied it from the video as is, just fixed a mistake with drop 0. The first I've mentioned is this error. It explicitly shows us that returning value is not just piece, but also something else. There is a reason for that, but more on this later. The second is piece drop 1. Drop function is returning string without the guarantees of length, but piece position should be defined by two components, column and row. It is also important that column and row are not any character, but limited amount of allowed values. And the third, taking an element from a string by index cannot always complete successfully, because piece can be an empty string. What leads us to the fact that the function is not working every time. Actually, it works every time, we just described it poorly. But let's return to the fact that returning value is not only piece. A bit of theory. A function is a way to assign an element from a set of input values to an element from the set of output values. A set of input values is called domain, and a set of output values is called codomain. An amount of elements in a set is called cardinality, and this will be enough for the continuation of our conversation to look smart. So, smart question. If we take a domain and a codomain, then how their cardinalities will be compared to each other? We have only three possible cases: less than, equal, or greater than. Let's look at them one by one. If domain is smaller than codomain, then a function can easily build relations between values. Even something will remain. If domain is equal to codomain, then we also don't have any problems. For each input value, an output value could be assigned. But it became interesting when domain is greater than codomain. What should we do with the reminder? The thing is that there is no reminder. Functions should assign an output value for each input value. Thus, we have only two options. We can either assign multiple values from domain to one value of codomain, like hash functions are doing, or codomain should have greater cardinality, what is actually will be the same as one of previous cases. Do you see where I am going with this? My first concern was about error function. There are programming languages in which you can hide a part of returning values by using exceptions mechanism. Although developers of Java language tried to fix this by introducing checked exceptions, but I see that developers not using it that much. So, here we see a clear decrease in cardinality. Type char have 256 possible values and type piece have only 2. In the current algorithm, we have distinct relations between a char and a piece. And this is the reason why we will avoid hash-like solution and will aim to extend codomain. There are several ways to do this, but here in Kotlin, I'm choosing to use a result type. It is already exists in standard library and it will be more expressive than, for instance, nullable type. By the way, in this way we also covered the problem with an attempt to take a first value from an empty string, but we will discuss it later. Right now, let's move on to the second problem. Drop 1 can return an empty string or a string with the wrong values. At first, we will deal with an amount of values. there should be 3 values, including the type of a piece. Otherwise, our code makes no sense and should not be executed at all. And to achieve this, we even don't need to introduce a new type. We already have the triple type. So we just need a function that will convert a string to a triple. And here you probably spot a problem with cardinality, right? String could have a number of characters other than 3. So its cardinality obviously greater than the cardinality of a triple of chars. That's why our function will return result type. Implementation of the function is trivial. Check the size and act assuming that everything is okay. Also, I will add a nice error message. Now we need to apply this function to the input value. It is easy to extract triple from result inside run catching context. We can just call get or throw. Class piece stores its position as a string, but actually there are 2 separate components. So we will fix it and we'll pass our values there. Time to deal with the types of column and row. As I said previously, not every value of type char is a column or row of a chessboard. So we need a structure that is able to limit the amount of possible values and also a conversion function. As for the structure, everything is simple here. In Kotlin we have enum type that is perfectly limits amount of available values. And it is not that hard to write a conversion function from char type to this enum type. Don't forget about cardinalities of domain and codomain and how to deal with them. Let's create enums for column and row, limiting ourselves with the values from the example, and also a conversion function. Interesting moment. I've used lowercase char function because the char type doesn't restrict a characters register, and I don't have a type like lowercase char that will allow me to explicitly describe what I'm expecting. Anyway, I don't care about symbols register. It depends on notation though. Also, I will modify the piece type in a way so it will use our new types, and also add the conversion function. And now a user of our from notation function will clearly see that not every string could be casted to a piece type, and we'll have to do something with it. A prompt, not get or throw. But that's not all. This code still has flaws, not to mention lack of proofs. That's why now we will reflect on how to write them and even avoid them. And I want to start this part inside out. Let's think how to prove that toChessColon is working. Do we really need to go through all 256 possible values? Of course not. We can go smarter and also make the code more reliable. We will reverse the function from char to chessColon and make a chessColon to char. Firstly, pay attention to the cardinalities of the domain and codomain. Secondly, because of exhaustive when, we cannot forget to add a relation between chessColon and char. Such a code just would not compile. Now let's reverse conversion. Essentially, we need to create a map instance using this toChar function, which will just create a key for each chessColon, thanks to associate by function in Kotlin. Then just search in this map. And in case of failure, just return an error. Obviously, create the map each time when we call the function is not that effective. So we will extract it to a context of the function. It will also simplify our proofs. So let's proceed to proofs. I will start with conversion from chessColon to char, because I have only 2 points regarding it. Does it provide unique char for each chessColon? And does it change since the last changes were made? Because it could lead to a backward incompatibility. For toChessColon function, we should confirm that it takes values from map, uses lowercase char function, and throws an exception if nothing is found. I assume that confirmation of exception message is too much, but I like it. Of course, we will do the same for the chessRow type. Create toChar function, create toChessRow function, and a context for it. Also, I will fix from notation function and will add proofs. The final touch. Let's do the same for the piece type. But there is a catch. The piece type is not enum, but nothing can stop us from creating an enum that will describe its type. In such case, we just do the same as we did for chess column and chess row. And after some fixes to from notation function, we get simple and reliable function. And don't forget about proofs. But behind all this change, we forget about from notation function itself. There is a mess now. We are creating anonymous objects and all thrown exceptions have no context. I mean, we barely can say which exception caused by which block of data. So let's fix it. We can create a new context which will just mimic the functions we are calling. Then adjust from notation function to use this context. Then we need to instantiate the context in main function. And let's add a wrapper for exception. The best idea I came with is to use recover catching and throw a wrapped exception. So you are very welcome to suggest your own ideas on how to do this. Well, let's end this block by creating a proofs for the new code. They also will highlight its problems. Even a try to write the proof reveals that we are tightly bound to triple function, what implicitly limits happy path domain. Also, the last when expression will only expand the amount of cases that we should check. To simplify everything a little bit, I will extract these functions to a context. Now a proof is just a demonstration of how from notation function behaves according to the behavior of different functions from the context. We even can go with parameterized test. Okay, enough code, let's reflect on it. I know that there are people who will say that this is too much, but I see reliability here. Now changes in our types are checked by a compiler, and changes to a function's behavior are breaking the proofs almost every time. Can you spot the issue? Such code will not surprise us with unexpected exception. Instead, it will carefully show what was wrong. In addition to this, extraction of dependencies to context made this code flexible by design. You can easily replace any part of the program. And now I want you to return to the part where we talk about types and functions, where we were understanding domains, codomains, and their cardinalities. I hope that this will help you to see your code from the different point of view. And of course, leave your questions in the comments below. I'm anticipating that we have a lot of stuff to discuss. When to look for a topic for the next video. Bye!